Sample inference dealing with proportions. We're going to start with sampling distributions for proportions for two independent samples. We'll take a look at how to calculate confidence intervals, sample size, and we'll end with calculating and interpreting hypothesis tests for two independent samples dealing with proportions. Our goal here is to compare the proportions of individuals with certain characteristics in two independent populations. Another thing that we could do is look at two independent populations and compare the percentage of people who maybe want to vote for a particular presidential candidate. When we're dealing with inference for two sample proportions, we'll actually have two parameters of interest. Our parameters are going to be P1 and P2, or PA and PB, just depending on the problem situation. The strategy here is to take separate random samples from each of our populations and then compare those by doing inference about the difference in the parameters. You know, all along we've been saying we had this population of interest. We'll call this P1. That's a parameter for that population of interest. And we've collected these samples. We call those P hat, a sample from that population. Well, now what we're doing is actually looking at two different populations that have parameters P1 and P2. We're taking samples from each, P hat 1 and P hat 2, and then we're looking at the difference in those parameters. Remember, when we do any type of inference, when we calculate sampling distributions, confidence intervals, or hypothesis test, we have to check our conditions or assumptions first. So for two sample proportions, for two independent samples, we have three assumptions. The first assumption is that we have two independent random samples from our populations, or if we're doing an experiment, we have two independent randomly assigned treatments. The key here is that these populations are independent of one another, or in the case of treatments, those are. Our second assumption is both of our populations have to be at least 10 times their sample size. And then finally, we have to check our assumption for normality. Normally, when we were doing one sample, we said N times P had to be at least 10. When we're looking at two independent simple random samples, we have to check normality for each. N1 P1 and N times 1 minus P1 have to be at least 5, and the same thing for our second population as well. Now, when we're dealing with sampling distributions, we need to be able to calculate the mean and standard deviation for those sampling distributions. Remember the formula from earlier this semester. The formula for the mean of a difference, the mean of x minus y, is the mean of x minus the mean of y. Now, today we're actually talking about sample proportions. So we're looking at the mean of p hat 1, sample proportion 1, minus p hat 2. Well, using our formula that we know here for the two independent means, we know the mean of p hat 1 minus p hat 2 is the mean of p hat 1 minus the mean of p hat 2. Well, if you recall, the mean of p hat is just the true proportion for that population. So the mean of p hat 1 would be p1, and the mean of p hat 2 would simply be P2. So we could rewrite this formula as P1 minus P2. So if we're trying to find the mean of P hat 1 minus P hat 2, or the difference in two sample proportions, it's simply P1 minus P2. We can derive the formula for the standard deviation in a similar fashion. Remember, we're talking about the standard deviation for a difference. So the standard deviation for x minus y, if you'll recall, is the square root of the sum of the variances of x and the variances of y, or the standard deviation of x squared and the standard deviation of y squared, which is what variance is. So if we were going to rewrite this, the standard deviation for p hat 1 minus p hat 2 is the square root of the sum of the variance of p hat 1 and the variance of p hat 2. Well, that requires us to remember our rules for the standard deviation of p hat. Remember, the standard deviation of p hat is the square root of p times 1 minus p over n. So if we square that, the variance of p hat is the square of the square root, or p times 1 minus p over n. So the variance of p hat 1 is p1, 1 minus p1 over n1, and the same thing for p2. So we could write this as the square root of the variance of p hat 1, p1, 1 minus p1 over n1, and the variance of p hat 2 would be p2, 1 minus p2 over n2, and this is the standard deviation for a difference in sample proportions. So let's take a look at our first example here. At Community Hospital, the Burn Center is experimenting with a new plasma compress treatment. A random sample of 316 patients with minor burns received the plasma compress treatment. Of these patients, it was found that 259 had no visible scars after the treatment. So this is all dealing with the individuals that got the plasma compress treatment. Now if we look at the next group, another random sample of 419 patients with minor burns received no plasma compress treatment. For this group, it was found that 94 had no visible scars after treatment. So this group had, we could call this placebo or the old treatment maybe. What is the shape and standard error of the sampling distribution of the difference in proportions of people with visible scars between the two groups? Well, if we're looking for shape, that's when we're talking about normal, skewed left, skewed right, uniform. Remember that standard error is simply our standard deviation when we're looking at sample data. So let's calculate the shape and the standard error for this sampling distribution. Well, the first thing we need to do is see if this distribution is normally distributed. To prove it's normal, we have to find N1, P1, N1, 1 minus P1, N2, P2, and N2 times 1 minus P2. Well, N1 was our sample size, 1. So if we look at our first sample, we had 316. And then P1 was the proportion of those who had no visible scars. That's 259 out of 316. Well, if we multiply that together, that's going to be 259. If we deal with N1, 1 minus P1, well, 1 is 316 over 316 minus 259 over 316. If we do that math, the difference here between 316 and 259 is 57 over 316. So we have 57. Sample size 2 was 419 and 94 had no visible scars. So that's 94 out of 419, which comes out to 94. N2 was 419. 1 minus P2, well, that would simply be 325 over 419. So this is 325. So we can say, since N1, P1, N1, 1 minus P1, N2, P2, and N2 times 1 minus P2 are all at least 5, the distribution is approximately normal. Now, the other thing that we wanted to calculate was the standard error of the sampling distribution. Standard error is simply our standard deviation when we use sample data instead of population data. Well, if you will remember, the standard deviation of p hat 1 minus p hat 2 that we've already derived is the square root of p1, 1 minus p1 over n1 plus p2, 1 minus P2 over N2. Well, I don't know the true proportion, P1 and P2. I only know my sample proportion, which is P hat. When we use P hat instead of P, that's when we call this standard error instead of standard deviation. So this is the square root of P hat 1, so that's 259 over 316. Well, and we can calculate. Let's do this first. P hat 1 is 259 over 316, which is 0.82. P hat 2 was 94 over 419, which is 0.22. So if we go back up here, let's go back a step. Let's calculate P hat 1 is 0.82. 1 minus 0.82 is 0.18 over my sample size N1 plus P2. 1 minus P2 is 0.78 all over 419. So our standard error comes out to be 0.0296. We've been able to calculate now the standard error and also the shape of the sampling distribution for community hospital. Now let's take a look at this same question, but let's talk about confidence intervals. If you'll recall the formula for a confidence interval that's on your AP statistics formula chart, a confidence interval is our statistic plus or minus the critical value times the standard deviation of our statistic. Well, the statistic we're looking at here is a difference in sample proportions. So this is P hat 1 minus P hat 2 plus or minus, this is a Z critical value for proportions. And the standard deviation of our statistic, well, remember, this is the standard deviation of P hat 1 minus P hat 2 that we've already derived today. So this is the square root of P hat 1, 1 minus P hat 1 over N1 plus P hat 2, 1 minus P hat 2 over N2. This is how we calculate the confidence interval for the difference in two sample proportions. Now remember, we're using a confidence interval to predict P, so we obviously don't have P. In those cases, we're going to use P hat instead of P. If you will also remember, all of this together is calculated to be our margin of error. And this right here is our point estimate. So our confidence interval is always our point estimate plus or minus our margin of error. Let's go back to example 1. Same situation we were dealing with before. We had those getting the plasma compress treatment here, and those that received no plasma compress treatment. Now what we would like to do is calculate a 95% confidence interval for the difference in proportions of people who had no visible scars between the plasma compress treatment and the control group. Now we're going to go all the way through calculating a confidence interval. So step 1 is to check our assumptions or conditions. The first is that we have two independent random samples of patients. And they are burn patients. So we could say of burn patients. The second is we need to look at make sure that our sample size, our population is at least 10 times our sample size. Now in this case, N1 was 316 patients, N2 was 419 patients, but both of them were burn patients. So since they're the same type of patient, if we add these up, then our total sample size was 735. So we can say the population of burn patients is at least 10 times our sample size, so 7,350. Now, had these not been the same type of patient, we would have to list them separately. But since they're both coming from the same population, which is a population of burn patients, we can compare them together. All right, so now we need to actually calculate N1, 1 minus P1. N1, P1. Let me go back. N1, P1. N1, 1 minus P1, N2, P2, and N2, 1 minus P2. And remember, if all we have is sample data, then that's the best that we're going to be able to use is P hat instead of P. So 316, this was 259 out of 316. We actually calculated these before, didn't we? So let's go back and take a look at what all those calculations were. 259, 57, 94, and 325. So 259, this was 57, 94, and 325. So since N1, P1, N1, 1 minus P1, N2, P2, and N2, 1 minus P2, are all at least 5, the distribution is approximately normal. Now let's calculate our confidence interval. Our confidence interval is our statistic, P hat 1 minus P hat 2, plus or minus our critical value, times the standard deviation of our statistic, P1, 1 minus P1 over N1, P2, 1 minus P2 over N2. Since we're predicting P1 and P2, all we can use is our sample data, so this is really standard error, which is an approximation for the standard deviation. Now, you need to make sure you know which way you're subtracting. That might matter to you. So for our purposes today, P1 is going to be those that received the plasma, and P2 is no plasma, just so I know kind of what it is I'm calculating. If you're going to use a calculator, this is going to be a 2-sample proportion confidence interval. So I think it says 2 prop for confidence intervals. So our confidence interval is P hat 1 minus P hat 2, plus or minus, we had 1.96 as our critical value for a 95% confidence interval. We actually used these calculations when we were calculating standard error, so we can go back and look those up in our notes or from our previous slides. And so we can calculate this confidence interval is going to be between 0.537 and 0.654. And then our final step here is our conclusion. Remember, this is a confidence interval for the difference in proportions. We were 95% confident, and we're predicting the true or the population. So we can say that the true or actual or population difference in proportions of people who had no visible scars between the plasma compress, and we'll call it the control group, is between 53.7% and 65.4%. So you've calculated a sampling distribution, means and standard deviations. We've proven our assumptions, and we've taken a look at a confidence interval. Now let's take a look at how to calculate a sample size that's needed. For example 2, suppose that researchers want to estimate the difference in proportions of people who are against the death penalty in Texas and in California. These are 2 independent samples, and probably people in different states have a differing opinion. If the 2 sample sizes are the same, and that's key here, What sample size is needed to be within 2% of the true difference at a 90% confidence level? Well, remember, within is our margin of error. So when we're looking at a confidence interval, our margin of error is our critical value times the standard deviation. Now, we were told we wanted to be within 2%, so our margin of error is 0.02. Our critical value at 90% confidence is 1.645, but we were told that our sample sizes are the same. So this would be the square root of P1, 1 minus P1 over N, plus P2, 1 minus P2 also over N. The sample sizes are the same. Well, if the sample sizes are the same, I have the same denominator. Now remember, my goal here is actually to calculate what sample size is needed. So I need to know N. We said before when we were dealing with one sample proportions that if we don't know the proportion, we use 0.5 to give us our estimate so that we could calculate the sample size. So this would be 0.5 times 0.5 over N. 0.5 times 0.5 over N. Well, now we're just going to do a little bit of algebra here. 0.02 equals 1.645. Under this radical, if we have the same sample size, we could add these fractions together. So 0.25 plus 0.25 all over N. Or this comes out to 0.02 equals 1.645 times the square root of 0.50 over N. Now, I do all of the calculations at the very end in our calculator because we don't want to introduce rounding errors. So the first thing we need to do is isolate the radical. 0.02 divided by 1.645 equals the square root of 0.50 over N. Don't put this in your calculator yet. We need to square both sides to eliminate the radical. Now, if I were to solve it like it looks, I would be solving for the reciprocal of N. I can't solve for a variable when it's located in the denominator, so we'll multiply both sides by N. And then we will find 0.50 divided by 0.02 over 1.645 all squared. N comes out to be 3,383. Remember, we always round up when calculating sample size. So our total sample size would need to be 3,383 people that we are polling. Now, we said in this case we polled the same sample size from Texas and from California. So our sample size would need to be 3,383 polled from each. All right, example 3. Researchers are comparing the effectiveness of 2 pain medications randomly selected for a group of patients who had been complaining of a certain type of joint pain. They divided these patients into 2 groups. So group 1 had 112 people. They received medication A, and 84 people said the pain reliever was effective. Pain reliever B had 108 people in the sample, and 66 people said the pain reliever was effective. So we're going to go back to what we've been doing in the last unit before this one, and we're going to construct separate 95% confidence intervals for the proportion of people who reported the pain reliever was effective. So we're going to calculate a confidence interval for medication A and a confidence interval for medication B. When we do that, the confidence interval we get from medication A is from 0.67 to 0.83, and the confidence interval we get from medication B is from 0.52 to 0.70. Well, if you were thinking about graphing those, if I go from 0.52 to 70 and I go from 0.67 to 0.83, here's medication B, here's medication A, and I want you to look at these intervals and describe for me how the proportion of people who reported pain relief with the two medications compare. Well, if you're looking at the confidence intervals, they overlap. So if the confidence intervals overlap, we would say there's probably not a significant difference in the pain relievers because we have an overlap in the confidence intervals. Well, now what I want you to do is calculate a confidence interval for one confidence interval for the difference in the two proportions. So now we're going to construct a 95% confidence interval for the difference in the proportions of people who may find these medications effective. So I want you to find a confidence interval for p hat 1 minus p hat 2, or we could say a minus b here, plus or minus my critical value times the standard deviation of my statistic. And we should get a confidence interval from 0.017 to 0.261. Now, if we were going to take a look at this, we would see, like let's say our null hypothesis, which we really haven't talked about yet, is that there's no difference in the proportions of pain relief, which means if there's no difference, P1 minus P2 is 0. Well, 0 is not contained in my confidence interval. Since 0 is not in my confidence interval, I would reject the null hypothesis, and I would say there is a significant difference in pain relief. But over here, we said there was probably no significant difference in pain relief because of the overlapping intervals. So which of those two conclusions happens to be correct? If the intervals overlap, we would say there's no difference in the proportion of people who reported pain relief. But if 0 is not in our confidence interval, we say there is a difference in the proportion of people who reported pain relief. So which is correct? What we would prefer to do is to do a comparison of the two independent samples and to do a two-sample confidence interval. There's a number of reasons for this. First of all, the confidence intervals could overlap and there still actually be a significant difference. Okay? When we're looking at two separate confidence intervals, in this case, we actually fail to reject the null hypothesis more frequently than when we do a two-sample hypothesis test. This means we have a decrease in power when we compare two confidence intervals and an increase in our type 2 error. So it is best to actually look at a two-sample confidence interval when we're comparing two proportions. Last but not least, let's look at hypothesis statements. Remember, we have to define P1 and P2 or PA and PB when we're doing hypothesis testing. Our null hypothesis is looking at whether or not there are a difference in the two proportions. So the null is always no difference, nothing going on here, nothing to look at. Now, for our purposes, we're going to look at whether there is no difference. Technically, we could also test whether the difference in a null hypothesis is exactly 2, and then we could write alternative hypotheses based on that. But for us right now, we're going to look at whether there's no difference. So where P1 minus P2 is 0. Now we could rewrite this. We could also add P2 to both sides. And another way for writing this is where P1 is equal to P2. If there is no difference, then the two proportions are equal. That's our null hypothesis. Our alternative hypothesis is that the difference between the two is positive. It's greater than 0. Or using algebra, that would be P1 is greater than P2. We could also have the null hypothesis where the difference is less than 0, or P1 is less than P2. Or the final null hypothesis is not that the difference is greater or less than 0. We just know there is a difference. It's not equal to 0. So P1 is simply not equal to P2 for a two-sided hypothesis test. Now, when we're calculating these, we are assuming that the population proportions are equal in the null hypothesis, right? that the difference is 0 or the two population proportions are equal. So we're assuming the variances are equal, so we pool the variances when we're dealing with two sample proportions. This is different than two sample means. When we pool the variances, we're actually taking a look at this calculation here. And your calculator, when you do this, will take care of these calculations for you. All right, let's take a look at our formula for a hypothesis test. Remember our test statistic, that's our z-test statistic, is our statistic, p hat 1 minus p hat 2, minus our parameters, which are p1 minus p2, divided by the standard deviation of our statistic. So this is, we said here we're assuming p1 is equal to p2. So we could say p1, 1 minus p1 over n1, p2, 1 minus p2 over n2. A couple of different things here. First and foremost, our null hypothesis is that this difference was 0. So we could simplify the calculation like this. The other thing is if we're pooling our variances and we're assuming in our null hypothesis that P1 is equal to P2, then we could also look here at the denominator, and this is just P1 minus P over N1 plus P1 minus P over N2. And then we could do a little bit of algebra to simplify. We could actually go ahead and factor out P1 minus P, since it's common to both of our fractions. And we could even simplify that further as the square root of P1 minus P and the square root of 1 over N1 plus 1 over N2. Again, this is really the algebra behind it. If you're using your graphing calculator, it does a lot of the calculations for you. All right, our final example. A forest in Oregon has an infestation of spruce moths. In an effort to control the moth, one area has been regularly sprayed from airplanes. In this area, a random sample of 495 spruce trees showed that 81 had been killed by moths. A second nearby area receives no treatment. In this area, a random sample of 518 spruce trees showed that 92 had been killed by the moth. Do these data indicate that the proportion of spruce trees killed by the moth is different for these areas? We're looking to check a difference or whether the difference is statistically significant. We do a hypothesis test. Step 1 is to state your assumptions or check your conditions. Pause the video now, check your assumptions, and then come back. Here are your assumptions. Our next step is to state our hypotheses. Remember, your null hypothesis is there's no difference, so P1 is equal to P2. Our question here was whether there is a difference or not, so this is a two-sided test. We're testing to see whether P1 is different than P2. Remember, we have to define our variables, where P1 is the true proportion of trees killed by moths in the treated area, and P2 is the true proportion of trees killed by moths in the untreated area. Now we need to do our calculations. When we're doing our calculations, we're responsible by naming the test by either name or formula. For formula, this is p hat 1 minus p hat 2 minus the difference from our null hypothesis, which was 0. This is the square root of P1 minus P over N1 plus P1 minus P over N2. On your calculator, this is a two-proportion z-test if you want to name it on your calculator. So we can actually carry out these calculations and we get our z-test statistic of negative 0.59. So if you're thinking about a normal distribution, here's negative 0.59, we're going to calculate our p-value. Remember, the p-value is the probability of getting the result you got, or one more extreme, that would be these shaded regions, since it's a two-sample test, if the null hypothesis was in fact true. Based on doing a normal CDF or our two proportion z-test on our calculator, our p-value is 0.5547. Let's assume that alpha is 0.05. Last but not least, we write our conclusion. Since our p-value is greater than really any reasonable alpha, we fail to reject the null. There is not enough evidence to suggest the proportion of spruce trees killed by moths is different in the treated and untreated areas. Alrighty folks, today we've covered sampling distributions, confidence intervals, calculating sample size, and hypothesis test when we're dealing with two independent samples of proportions. Have a great